Hey everyone, we're back, and guess what we're going to do today? We're going to study the revolution of the Earth, and it's going to be in two videos. This one, I'm going to go through the slides and show you some animations, and then in the next one, I'm going to actually model what you're going to do as you're drawing on your sketch, on your model, okay? So we've studied Earth's rotation and the phenomena that are created by that. Now we're going to study the phenomena that are created by Earth's revolution around the sun. It's very easy to get the words rotation and revolution confused. Just remember, rotation has an A, that's the spinning on an axis. Revolution has a U, and we revolve around the sun. So that's how you can easily remember the difference between the two. So remember that the Earth revolves around the sun in an elliptical shaped orbit, and one complete revolution takes 365.25 Earth days, and that is considered to be 1 year. In conjunction with the axis tilt, the axial tilt of the Earth, and we know that the tilt is always parallel to itself, this is what causes the change in seasons, and that's what we're going to get into today in detail. Now, if the axis wasn't tilted 23.5 degrees relative to the perpendicular of the orbit of Earth, there would be no seasons. We would have the same weather pretty much all the time. All right, all places on Earth that have the same weather all the time, because there wouldn't be a varying degree of insolation. All right. If there was a greater tilt, so if it was greater than 23.5 degrees, we would have even more extreme seasons. So our winters would be colder, our summers would be hotter. All right, so there was a greater tilt, more extreme seasons and temperatures, no tilt, really no seasonal changes. Okay, so here's a nice diagram relating what we did in elliptical orbits versus what we're going to do now regarding the tilt of the Earth. So as you remember, at perihelion, which occurs around January 3rd, we are closest to the sun, and at aphelion, we are furthest from the sun, and that occurs around July 4th. Now, I need you to understand that perihelion and aphelion are measured in relation to the elliptical orbit of Earth. The solstices and the equinoxes are measured in relation to the axial tilt as it is relative to where the sun is. Is the North Pole tilted towards the sun? Is the North Pole tilted away from the sun? Is the North and South Pole tilted neither away nor toward the sun? Aphelion, perihelion, and the solstices do not jibe. They are not related to one another. And more importantly, aphelion and perihelion have nothing to do with why we have seasons. Because as you can see, when we're closest to the sun at perihelion, it's actually the northern hemisphere's winter. And when we're furthest from the sun at aphelion, we're furthest from the sun, that's actually our summer. So if somebody tells you like, oh yeah, we're closer to the sun in the summer and we're further from the sun in the winter, you say, no, if that was true, then the northern hemisphere seasons would jibe, and they don't. They're opposite. So we know that that's not the reason why we have seasons. So what phenomena does the Earth's revolution around the sun create? Oh, by the way, one more thing. Question, how many degrees are in a circle or an ellipse? How many degrees are in this circle or ellipse? 360. How many Earth days does it take for this Earth to go around the sun? 365. Okay. So 360 degrees in 365 days. Approximately how many degrees does Earth move through space per day? 360 degrees in 365 days. That is approximately 1 degree per day. So every day that the Earth revolves around the sun, it moves approximately 1 degree in its orbit. Make sense? Okay. So the phenomena that the Earth creates as it revolves around the sun. Okay. I need you to understand and remember that all of what's going to happen, these phenomena that are created by revolution, these phenomena that we're going to study today are also related to Earth's tilt on its axis and the parallelism of that tilt. Okay. So the first thing that it creates are these very special days of the year called the solstices and the equinoxes. Okay. On the solstices, which in the summer is June 21st approximately, okay, and in the winter is December 21st approximately. That can vary by a day, okay? Um, on June 21st in New York, we have approximately 16 hours of daylight and 8 hours of darkness at our latitude. And the sun, it will be directly above the Tropic of Cancer, which is 23.5 degrees north. On the winter solstice, which is approximately December 21st, it's the exact opposite. The sun is directly above the Tropic of Capricorn, which is 23.5 degrees south. Now, on the equinoxes, equi means equal, and nox means night. So equinox means equal night. What they're leaving out is the day, okay? So on the equinoxes, there are equal amounts of daylight and darkness for the entire Earth. Everywhere on Earth is experiencing 12 hours of darkness and 12 hours of daylight, okay? Except the poles where it's twilight. At the poles on the equinox, it's pretty cool. The sun just hugs the horizon for 24 hours. It goes around the horizon for 24 hours. It's pretty cool, right? And on the equinoxes, the sun is directly above the equator, all right? Now, the fall or autumnal equinox, it happens about September 23rd. And the spring or vernal, verde or vern means green. So the green equinox is like when in our beginning of spring, it's when everything comes back to life and turns green. That happens approximately March 20th. It could be the 19th in some years. It could be the 21st in some years, but that's the approximate date. So these are the dates that you can use for these special days. All right. Now, why are these days special and how are they created? Well, that's due to this diagram. All right, now what I'm going to show you is a moving version of this diagram. All right. Okay, and we'll go here. Okay, so, okay. So this is an animation of the Earth and its orbit around the sun. So the first thing I want to show you is that, see the orbit, if we were looking at it from exactly the side, here would be the sun and here's the Earth. Disclaimer, drawing is not to scale. Okay. But what we can do here is we can drag this Earth around the sun. We can drag it around the sun. But as you can see, when the Earth is over there, you see how it's hidden behind the sun? And when we bring it over here, you see how, if I put this back, you see how the sun is hidden by the Earth? And then it goes behind the Earth, sun, and it should be over here, okay? That's kind of a pain, all right? That's kind of a pain. So what we want to do is we want to give it depth. So in art, you know how you give it depth, you put it at an angle. So what we do is we put this at a little bit of an angle. And then we can see when the Earth is to the right of the sun, we can see when the Earth is back there, we can see when the Earth is to the left of the sun, and we can see when the Earth is on this side of the sun from us, okay? So I want you to take a look at the North Pole and the South Pole. Just keep your eye on that North Pole. As the Earth revolves around the sun, note that the North Pole is always pointing to the same place in space. So if you take a look at this axis, as the Earth revolves around the sun, the axis is always parallel to itself. That is called the parallelism of Earth's axis. And the North Pole always points to Polaris. All right. So the cool thing about this animation is this is a close-up of the Earth with the North Pole and the South Pole always straight up and down. And what's going to move here is the day-night line, okay? The separation between day and night on Earth, when we draw it, this line, this separation line is called the terminator, okay? That's what it's called. It's called the terminator, all right? So when you're asked to draw the terminator, you're drawing the day-night line, okay? And what you're going to do on the dark side of the Earth on the terminator, you're just going to shade it in lightly to show that that side of the Earth is in darkness and the other side of the Earth is in light, is in daylight. Now, what do you notice? Well, the side of the Earth that's facing the sun is lit up. Duh. Thank you, Captain Obvious. Okay. And this down here, okay, so this is the Earth traveling around the sun. This over here is the day-night line, and where the sun's rays are directly over Okay, we're going to get to that in a second. This shows the rays of the sun at the observer's place. So as you can see right now, you see these are the rays of the sun coming down and hitting the earth. The sun is at this person's zenith. Remember what the zenith is? It is the point directly above you, okay? How do I know that? Because the rays of the sun are perpendicular. So these are the rays of the sun, and that's the Earth's surface. The rays of the sun are perpendicular to Earth's surface. They're making a 90-degree angle. Okay, now check this out. When I move this person, I'm going to move this person towards the equator. Ooh. Are the rays of the sun perpendicular to Earth's surface anymore? No, they're not. Okay, they're at an angle. I'm going to move this person down to the Tropic of Capricorn. Whoa, that's a big angle. I'm going to move this person down to the Terminator. Oh, the rays of the sun are like parallel to the ground. That means the sun is on the horizon. I'm going to move this person to the South Pole. Oh, it's dark, right? I'm going to move this person up to the North Pole. Oh, it's daylight. Interesting, right? Okay, so that's how this animation works. And I can turn on labels here too. And that will tell me the North Pole, the Arctic Circle, the Tropic of Cancer, the Equator, Tropic of Capricorn, Antarctic Circle, and South Pole. All right, and if I turn them off and I put the person on the line kind of lights up there, okay? All right, so now we're going to get into this. Now this is a little bit more complex. So what's the old memory aid? The sun rises in the east and sets in the west. Yes and no. Okay. Generally, the sun rises in the eastern part of the sky and sets in the western part of the sky, but it only rises due east and sets due west 2 times a year, 2 days. That's it. 2 days. That's it. Okay. Let's go to June. What is it? Today's the 3rd. Okay. Let's go to June 3rd. Okay. Have you been noticing that the amount of daylight's been getting longer? Yeah. Okay. Me too. I love it. Love it. Love it. Love it. Okay. Let's start the animation. Oh, wait, no. I got to change it. I got to go back to June 3rd. And I'm not going to step by day. I'm going to go continuous. Okay. So let's see what happened today. Let's start the animation. There's the sun setting. There's nighttime. And I'm going to stop it right there. Okay, I'm going to go back to sunrise. Okay, there's the sun rising. Where is the sun rising right now? Is the sun rising due east, which is right there? No, the sun is rising in the northeast part of the sky, right? The sun's rising in the northeast part of the sky. Then the sun crosses our meridian. Okay, this is solar noon, when the sun crosses our meridian. Okay, you notice the sun is in the southern part of this observer. So when we're in Katona, right, we have to look south to see the noon sun. And as you notice, this person's shadow is in the north. Now, I know it doesn't look like the sun's in the south part of the sky, but it is. You see? The person is looking south to see the noon sun. You see that? Okay. And then, watch what happens now. The sun's going to set. I'm going to start it again. Boom. Where is the sun setting? Is the sun setting due west? No. The sun is setting north of west. Okay? This yellow line is called the sun's path for today. So the sun's path today, the sun rose north of east, went all the way to the southern sky, and then set north of west. That's a really long path. The sun was out a long time today, wasn't it? It was. Okay. Now I'm going to make this go to, I'm going to put the sun back to solar noon. Okay. Boom. Okay. And I'm going to change this to June 21st. And I just want you to watch what happens to the height of the noon sun. I'm just going to change it to June 21st. See how the sun got a little higher in the sky? Got a little higher in the sky, right? Okay. Watch what happens when you go from June to September. What's happening to the sun? It's getting lower and lower and lower in the sky until this is now the autumnal equinox. This is the only day of the year where the sun rises, well, one of the 2 days of year where the sun rises due east. See that? On this day of the year, the sun rises due east, exactly east, and sets, watch this, sets due west. It sets due west. That's one of the 2 days of the year that it does that. The other day of the year that it does that is March 21st. Okay. Now here you get 12 days of light and 12 hours of light and 12 hours of dark. Equinox, right? Now what's the shortest number of daylight hours of the year for the northern hemisphere? You got it. The winter solstice, December 21st. Let me get there. Okay. Here's the sun's path on December 21st. Now, where does the sun rise? Whoopsie. Let's go back. Where does the sun rise? The sun rises south of east, right? The sun rises south of east, takes a quick hop to the southern part of the sky at noon when it crosses our meridian. Look how long the shadow is. And sets south of west. So, rises south of east, goes to the southern side, sets south of west. South, 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 right? Quick path. The sun's always in the southern part of the sky. But in the summer, why are the days so long? Because the sun rises north of east, goes all the way to the southern sky, and sets north of west. That's a long sun path. Now, what's happening is the sun is out a long time. The duration of daylight is very long starting this time of year. What do we call sunlight? Incoming solar radiation, insolation. Why does it turn into the warm summer months? Because number one, the duration of insolation. Whoa, duration of insolation. Missile Gorman, what's that? Okay. The length of time the sun is shining on the earth in the northern hemisphere. The duration of insolation is long starting this time of year. That allows the land and the water in the northern hemisphere to heat up. Duration of insolation. Not only is the duration of insolation long, but the intensity of the insolation is very strong. Okay, what do I mean by intensity? I mean the sun is higher in the sky. Its rays are more direct. In the dead of our winter, if you go to the Caribbean on vacation, you got to slather on the sunscreen. Why? Because the sun is very high in the sky and it's very strong. When is the sun strongest? At solar noon. That's when the sun is highest in the sky and its rays are concentrated on us. Okay? Whereas in the winter, I mean, you could go out at noon and probably not get sunburned because the sun is so low in the sky. Why does it turn into winter? Well, look at the duration of insolation. Short. It's like 8 hours. It's like, okay, the sun's not out that long. I don't have that much time to heat up. In addition, the intensity of the insolation is very weak because it's low in the sky. The rays are spread out over a large area of land. So it's all about the duration of insolation and the intensity of the insolation, right? That's why we have seasons. And why does the duration and intensity of insolation change? Because of Earth's tilt and the parallelism of the Earth's axis. Okay, let's look at that in this animation. Now, this is really good. This animation keeps the Earth upright and changes the direction of the sun's rays. So let's start. That's the September equinox. Now, this is coming up on our June solstice. Our winter solstice. Where's the most direct insolation? Where is the sun directly over? Tropic of Capricorn. Who has 24 hours of sunlight? Everything from the Antarctic Circle to the South Pole. As the Earth rotates, this whole area of Earth down here has 24 hours of daylight. What's going on between the Arctic Circle and the North Pole? 24 hours of darkness. So that the southern hemisphere has intense insolation and a long duration of insolation. That's the beginning of their summer. beginning of our winter. Let's keep going. As you go from December to March, okay, coming up on that equinox, we're going to stop it, the vernal equinox. Where is the sun's direct rays? On the equinox, they're directly over the equator. Insolation is divvied up between the northern hemisphere equally. We're transitioning now. We're going from winter to summer in the northern hemisphere and summer towards winter in the southern hemisphere. So it's our beginning of our spring, beginning of the southern hemisphere's fall. Okay. Then we're coming up on the first day of our summer, first day of the southern hemisphere's winter. There we go. Where is the direct rays of the sun? Well, the sun is directly over the Tropic of Cancer, 23.5 degrees north. Between the Arctic Circle and the North Pole, 66.5 degrees north and 90 degrees north, 24 hours of daylight. Between 66.5 degrees south, which is the Antarctic Circle, and 90 degrees south, 24 hours of darkness. Right? The northern hemisphere has a greater intensity of insolation and a longer duration of insolation, heating up the water in the northern hemisphere, heating up the land masses, getting that summer going. All right? And then, as the Earth continues around the sun, that axis stays parallel to itself. The rays of the sun change. There's our autumnal equinox again. So now we're transitioning seasons. Okay? And here's what it looks like in terms of sunrise and sunset. So let's go to sunrise. If you have a view of sunrise, you're going to notice, hey, I go out in the fall, the sun's rising over there. I go out in the summer, the sun's rising over there. I go out in the winter, the sun's rising over there. Okay? The sun rises south of east in the winter, and it goes to the southern sky and sets south of west. On the equinoxes, where does the sun rise? The sun rises due east on the equinoxes. And where does the sun rise in our summer? If you go out right now, it's rising north of east. The sun's then going to the southern sky at noon and then setting north of west. So let's take a look at sunset. Same thing. The place of sunrise and sunset varies. Generally speaking, does the sun rise in the eastern sky? Yes. Generally speaking, does the sun set in the western sky? Yes. But the position changes. Again, why? Because the Earth is tilted on its axis, and the axis remains parallel to itself as it revolves around the sun. Okay? So, what I'm going to do now is I'm going to stop this one, and I'm going to create another video modeling how you're going to draw on your diagram of the sun, of the Earth revolving around the sun. Okay? See you in a minute.